Greetings to all the participants of this faculty development program. My name is Dr. Gaurav from Bengaluru. First and foremost, I would like to thank IIT Goa for giving me the opportunity to give the talk on this topic, demand-driven solutions in communication intelligence. So, because I was selected as a resource person from the industry, I have selected a topic which can be related to the activities of industry, as well as it has got a lot of theoretical connection of implementation of the finding, research finding. So I hope this particular topic is of interest to you as a academic fraternity. So here it is. I would like to start the topic. Take you to the topic of the communication intelligence. I would like to take you to an event which has occurred way back in 1941. The day was 7 December, when a completely unprepared fleet of US Navy was attacked by the Japanese Air Force. And it was a very devastating incident, and where very, very massive amount of loss was incurred by the US Navy. And in fact, this event has actually changed the course of history. US is known to be very, very well equipped in terms of their military warfare and the communication technology and the spies, everything. But somewhere there was a gap, and this entire event, which was planned very meticulously by the Japanese forces, was somehow unknown to the US forces. That has occurred to this massive catastrophe, and it was never anticipated by the US forces. So there was a huge speculation regarding this particular event as to what could have been done to avert this particular incident. So finally, as usual, the demand on the intelligence, that is the communication intelligence, could have averted has came to light. So where the importance of the communication emitted by the enemy could have been a huge source of information to know what could have been the next move of the enemy. So this involves not only a lot of involvement and deployment of the forces, but at the same time, competent technology to do the interception of this kind of communication, to analyze and to really understand what is the communication is all about. Because all this communication at the wartime used to be encrypted. So the requirement is very clear. War is going on, and there could be any other move at any point of time by the enemy forces. So Allied had to take a very, very strong and concrete step to avert this kind of incidents. And also, as we know, war is not fought only by the weapons. The advantage of any side comes with the prior knowledge of or prior hints of what the enemy could do in the next instant. That is the reason that huge demand came for interception of the enemy communication, the break of that, and to finally get the intelligence out of that. So from this incident, we have seen that there is a huge demand, and which we can say it is an unprecedented demand for break of secret communication. And then it must have to be done. There is no real physical limit test, or there is no feasibility analysis test to achieve this kind of requirement. It has to be done. It is the need of the hour. And it is required immediately. There is no specific lead time that we have. Normally, we do during the project planning. So it's a huge demand that has to be met in a very, very short span of time. In fact, it is within zero time. So results are highly, highly time sensitive. So in this scenario, it's a very big challenge for in terms of technological maturity at any point of time, because we have to build something which is a very way ahead of time, and also it's a quantum jump in technology. So what are the things that goes into the development of this huge amount of technology within a very short span of time, and what are the practical difficulties, and how it is actually coped up, and what are the planning normally done. So this is what I would like to cover in this particular topic. And just this particular introduction, I hope will make the things or make the tempo up to go into the theoretical aspects of the topic. Well, the demand has brought us into the war between the Enigma machine and the requirement to break the Enigma machine. Now, what is Enigma machine? It is the backbone of German secret communication, where using a combination of the relays and mechanical switches, the machine used to generate a sequence of secret codes, and which used to appear completely random when it is seen by a simple interception machine. So, for a very long time, I should say in several months, the researchers and mathematicians from the Allied forces could not figure out exactly how the Enigma machine functions until they got their hands into a captured Enigma machine from one of the German submarines. And then they could do some level of reverse engineering to figure out the basic principle of operation of Enigma. And with that, with a combination of a machine called Colossus, it was built with again a huge combination of electromechanical switches and relays, with the help of this captured German Enigma machine, they were able to first time figure out the first level of code message, which was decoded in clear text. So after that, the calibration and further fine tuning of the Colossus machine took a total of about 6 months. And with this, the turn of the events has completely changed, because now what has happened? The Allied is able to intercept the secret communication of German and their Allied forces, and at the same time they are able to decode the text, and they were able to know, or they can collect intelligence, very very vital information regarding the next move of their adversaries. So that this gives a very much actually military age over their enemies, and this has turned the events of the World War II. In India, we have our own present day context for initiating the research and implementation of communication intelligence systems. We all remember the pictures of 26th November 2008 when Mumbai was attacked by insurgents. That was a very sad incident, but it has given a big trigger for creation of our own technology base in this particular area, so that any communication which is used by the insurgents, like satellite communication, mobile communication, or VHF radio communication, microwave communication, can be intercepted with a versatile system. And finally, we can collect intelligence in a homegrown system, so that our intelligence agencies can reliably gather information and take necessary actions much before any adverse incidents happen. So this is one of the demands that we have faced in the recent past. The demand, in short, can be told that the system has to detect, estimate, process, and analyze any sort of enemy communications or adversaries communication, so that it can accumulate the intelligence, and based on that, the intelligence agencies can take actions much in advance, or prior information based on that can be strategic in nature, which the forces or the different law enforcement agencies can take the action towards that. As we have seen the paradigm of communication intelligence, it all started with the interception of analog communication radios way back during the era of the communications that used to be analog. And simple tuning of the frequency of transmission, the intelligence from the enemy transmission could be gathered. Then we have already seen the war between the Enigma machine and the Colossus, and we have also seen how it has turned the events of the World War II. And now we have come to the era of digital communication with different forms. Let it be mobile communication, it could be satellite communication, or there are many different numerous military communication equipments. So, in just the way of attacking the problem in present day is also different. Here we have to think about a process or machine which can be versatile and flexible enough to address all these different types of communication, or we should be able to attack the problem in specific areas. So it all depends on the analysis of feasibility, time, and different constraints for the requirement. So in the modern day comment era, look at the challenges. We have microwave PSTN links where communication can go, satellite communication links, military man-pack radios, military tactical radios, cellular, satellite mobile phones, aviation signals, internet traffic, broadcast services, blah, blah, blah. So many varieties of target signals can be taking potential signals by adversaries and insurgents. So you can just make out the challenge of intercepting the huge different types of sources, gather information, store it, and finally make use of that information for strategic intelligence gathering. So let us have a look at the signal decoding or processing tree for a typical comment system. At the forefront, we have the carrier scanning and detection block to detect the active carriers. Once the active carriers are identified, we can take on each of the active carrier to further process by starting with the demodulation process. Once we demodulate the signal successfully, we have to strip out the forward error correction, then followed by the blind descrambling. Then we have the deframing process. And finally, we encounter the protocol level tree where actually the payload data in terms of voice or text or video or any kind of intelligence message can be finally decoded. So this is about the complete chain. Now, just note one particular keyword here, that is blind. So as we have seen, unlike the conventional communication system, comment is blind because we don't have any prior knowledge of any of the parameters of intercepted signal, right from the carrier scanning and detection down to the final stripping of the final intelligence. So we have to walk layer by layer in a progressive decoding process where we first resolve the first and the foremost layer, then followed by the next layer, and so on and so forth. So the blind process is all about complete unaware of the parameters of the communication signal. So what happens in conventional communication and what is the scenario in blind comment? So here it is. Mainly conventional communication has the knowledge of the parameters. It could be carrier in carrier or single carrier, modulation, symbol rate, coding, scrambling, frame protocols. However, all these parameters in the context of blind communication intelligence is unknown. Secondly, the channel plays a very important role in in communication intelligence as well as in normal conventional communication. However, the major difference in between these two scenarios is in conventional communication, we can have a pilot sequence which can aid to equalize the signal against multipath and fading effects, whereas we don't have that luxury in communication intelligence. So we cannot expect a data-aided scenario where we can have a pilot signal. So the strategy for communication intelligence is completely different. We a whole lot of approaches starting from the first layer of demodulation, decoding has to be completely different. Here. The last one being a recent challenge in the communication intelligence area, which is sharing of the spectrum by two transmit and receive pairs. So this is like an interfering pair of signals which is intercepted by the system and finally need to be separated out. Well, this is another topic for discussion. Mainly, we would like to highlight the basic challenges in each of the layer. So what we will do, we will try to restrict our discussion within the blind demodulation and various theoretical research findings and how these are associated and implemented in the communication intelligence system. Demodulation block involves estimation of symbol rate, then estimation of various different parameters towards automatic modulation classification, and which finally leads to the real-time demodulation. The challenges involves most of the cases we encounter signals which is having very poor signal to noise ratio, and the signal many cases, many occasions comes with huge fading and under noisy conditions. And that finally leads to the requirement of blind channel estimation and equalization. So let us first examine the signal model of the received carrier, which is a function of the carrier frequency offset, the phase offset, the channel, the symbol time period, the timing offset, and the noise. So once we successfully demodulate the received carrier, we will be left with the baseband signal model, which is again a function of the signal amplitude, the phase offset, and noise. So in the context of the various transmission scenarios, we have the simplest case of signal attenuation when we don't have any reflections or any fast fading scenarios. So the scenario of the received signal is only the amplitude variation. Then we have the scenario of static multipath fading where during the observation interval, the parameters doesn't change. And in this case, we have the amplitude variation, the phase offset, and the noise. These are the unknown and random factors to be considered. Now, finally, the most challenging scenario, which is a time varying channel. And of course, the target or the reception platform must be a moving platform in this particular case. So we have again the randomly varying amplitude, we have a randomly varying phase, and the noise. So these three scenarios, we have different approaches. So first, to attack the first two scenarios, which are relatively simpler compared to the third scenario. So our next study and approach towards parameter estimation will first concentrate on these first two scenarios. The first parameter that we take on is symbol rate of the received signal. We have the scheme of estimating the symbol rate using the features called spectral correlation function, then the spectral correlation coefficient that is derived from the spectral correlation function itself. When we see the plot, 3D plot between the cyclic frequency and the spectral frequency domain, we see various artifacts generated at the symbol rate. So this particular features was helpful because it is immune to the noise scenario as well as the fading scenario. So as we have seen, the artifacts that is generated towards the cyclic frequency axis shows the carrier frequency as well as the places where we have the symbol rate. So this is one proposal from our implementation where irrespective of the scenario of very low signal to noise ratio as well as multi-path fading, we should be able to determine the symbol rate. Well, if you see the plot for the spectral correlation coefficient, in the fading scenario, we have seen the spreading of the cyclic components due to very reason of the fading components. So if we see the cross section from the cyclic frequency domain, we have seen there are a lot of ambiguities. So cyclic profile of this much ambiguity cannot give us a symbol rate. So we have to come out with certain other features derived from this particular feature. So next we have the requirement for certain feature which gives us an unambiguous determination of the symbol rate. In this context, we have defined a new parameter called cyclic domain power profile, which is the aggregate power along the spectral frequency axis. By aggregating the power, cyclic domain power, we are able to derive this parameter. And this parameter is robust in the sense, even in the fading scenario and with very low signal to noise ratio conditions also, this preserves the symbol rate parameter. So by searching the peak of the symbol rate, we were able to exactly pinpoint this specific parameter. So the accuracy of this is very high in fading, various levels of fading and noise scenarios, which we will show the results in the next coming slides. So this is the performance of the proposed new symbol rate estimator, where we have compared the mean square error of the proposed implemented method with other methods which are ML-based methods and cyclic autocorrelation-based method. Here clearly we have seen the advantage of the current estimator at very low SNR, and we have seen that the plot is at various channel conditions, and we have seen the robustness against the various channel impairments and signal to noise ratios. After estimation of the symbol rate, the received carrier is demodulated into the baseband, and we employ the quasi-hybrid likelihood ratio test as the modulation classification method, in which we have this log likelihood function involving unknown quantities, unknown parameters as noise, the signal amplitude, and the phase offset. Now, the modulation classification is done with the decision rule by maximizing the log likelihood function with respect to the pull-up modulations. Towards the parameter estimation for the modulation classification, we have employed the expectation maximization clustering algorithm using the model as Gaussian mixture model. And expectation maximization algorithm provides the estimates of the cluster centers and the noise variance From there, we derive the parameters for the amplitude and the phase offset. Now we can see in this slide uh, the representation of a 16 qm signal as a Gaussian mixture model, where we have seen the histograms of each of the clusters of the 16 qm signal. And by doing the expectation maximization clustering method, we are able to estimate the center frequencies of this every modulation. And now the requirement for expectation maximization algorithm is that we have to predefine the number of clusters for the convergence of this algorithm. With this, we need to actually determine what is the number of clusters for uh, applying expectation maximization algorithm. So EM convergence needs the prior information of the number of clusters. In this example, we have shown the clustering of a QPSK signal with some phase offset. As after the result of convergence, we have seen the cluster centers of the 4 clusters of the Gaussian cloud. Now, if you see one of the clusters, the plot of one of the clusters and the histogram representation of the elements of this cluster, and if we examine the Gaussianity by determining the kurtosis value, we have seen that if it is a true Gaussian cluster, the kurtosis value will be towards 0. But in a different scenario where we have predefined the number of clusters as 2, and the modulation happens to be QPSK modulation, where we have actually 4 clusters, but the predefined number of clusters is 2. So the resulting histogram representation of the clusters and the resulting kurtosis values will be much higher than 0. So this shows that this is a non-Gaussian cluster, and it's an indication that something is not placed properly. So from these two cases, we have seen that the case for which the kurtosis value is minimum or towards 0 is the best fit for the number of cluster centers. So in this particular case, it is 4. So we have the modulation order as 4. So this particular algorithm we can extend to any number of pool of modulations. So only thing is that we have to apply this particular clustering method every time for every hypothesis. And finally, there will be one point where the cluster centers for a specific number of predefined clusters will give you the best Gaussianity. So that will be the point where we can define that the number of clusters actually is so and so forth. So once we estimate the cluster centers of the target signal, we can approach for determination of the signal amplitude and the phase offset. This is a geometrical process, and we have seen here the yellow dots indicates the estimated cluster centers of the target signal. In this case, it's a 16 qm signal, as we have already seen. And the red dots indicates the ideal constellation, which is nothing but normalized normalized constellation model of this particular hypothesis, that is 16 qm. Now we compare this amplitude of the cluster centers of the outermost cluster center with the ideal constellation model. Now that gives us the ratio of these two gives us the signal amplitude. And next we can again have the phase difference between these two vectors, which directly gives us the estimate of the phase offset. But this is a simple conversion, but it gives fairly well simplistic estimate of these two parameters, which is required for our log likelihood function determination. Now, if we apply the correction factors into the received signal, with these two parameters of amplitude and phase offset, we can see that we can correct the signal, and the received cloud nearly coincides with the ideal constellation pattern. Performance of the modulation classification is done by the probability of correct classification against SNR values. Now, in these results, we have shown that the results obtained for different modulations for BPSK, QPSK, 16 QAM, and 32 QAM against the results for the cumulant-based methods. That is one of the feature-based methods for the same modulations. So the results are very encouraging. We have seen that the results are much better for lower SNR regions. And this is the main advantage of this particular blind estimation method, is utilized for this communication intelligence block for blind demodulation. So there is another way of looking at these results for the modulation classification using the quasi-log likelihood ratio test with semi-blind approach. In our case, we have the unknown parameters as the amplitude, the phase offset, and the noise. And we have seen that the red line, which is towards the complete blind curve. However, there is an improvement because we have actually assumed certain parameters like the frequency offset, the timing offset, etc., as a known parameter. And the scenario also we have seen where it could be a non-blind scenario, which is not practically feasible, but to show the comparison, we have plotted this non-blind scenario along with some semi-blind scenarios where certain parameters are known. So this plot is to give the idea of relative performances between blind and the non-blind scenario. Well, we have attained certain amount of success, which we can say in the blind demodulation block. Now, the first scenario is that we have the propagation loss where we don't encounter much of multi-part effect. Typical example being interception of signal from satellite, where we don't encounter any reflections from buildings or trees or vegetation. So this is a pure case of resolving the amplitude uncertainty under the Gaussian noise. Now, the second scenario, which is a static target and which is encountered with multi-path fading due to reflections from buildings and vegetations and military vehicles and so on and so forth. In this case, with the observation interval being fairly static, we have the amplitude uncertainty and the phase offset under Gaussian noise, and we have fairly well resolved this. And the first scenario being the subset of the second, so we can say it is well resolved within these two scenarios. So the channel still persisted for the cases of complex channels, where channel variation is observed during the observation interval. Now, this is a typical scenario where the target is moving or the interception platform is mounted on a moving platform. Scenario is again for estimation of the channel and which results in estimation of the amplitude uncertainty and the phase offset. Of course, under the additional impairment of noise. So the conventional equalization approach which comes into our mind in conventional communication system, which is by applying the measures like LMS-based equalizers, which employs pilot sequence and other methods like decision-directed approaches and all. So, however, as we have seen, we are completely blind and we don't have any parameters. Even the modulation scheme is also unknown. So, in this scenario, we have to have completely different set of approaches. So, let us get into that, how we mitigate this, and towards a blind scenario, how we formulate the solution. Let us discuss the approach in detail. First, start with the comparison between the conventional and the blind scenario for equalization. Now, when we talk about equalization in conventional communication, first approach that comes to our mind is LMS-based equalizers with training sequence. Now, same thing is not applicable for a blind scenario because we don't have the knowledge of modulation and the training sequence. However, blind equalizers has been employed in conventional communication, the likes of decision-directed LMS equalizer, where at least the knowledge of modulation is required. So, because we are again blind, we cannot apply this scenario because the very lack of information regarding the modulation scheme. Other approaches for correction of phase and amplitude uncertainty in conventional communication involves the constant modulus algorithm. Whereas in blind scenario, the same thing is applicable. However, for very noisy scenarios, this may not give the adequate and desired results. So we still need a total different set of approach or a combination of different utilities which is used in conventional communication. So we have to devise a different method. So let's see how it is done. So here we have adopted a totally different scheme, and this is a cascading stages of modified constant modulus algorithm equalizer and modulation specific decision directed LMS equalizers. Now, as you have seen from the scheme, the first stage is a modified constant modulus equalizer, and the output of that equalizer is different branches of modulation specific DDLMS stages, and each of the DDLMS stages designed as per the candidate modulation scheme. Now, just observe towards the right of this diagram, we have shown a decision function for BPSK and QPSK for the DDLMS block. So these are the decision boundaries for a normalized constellation value, which is 0.7071 towards the higher side and minus 0.7071 for the lower side. So if we extend this particular function for other modulations, we can have different levels of decision values for different modulations. So this is the basis of this modulation specific DDLMS algorithm. And the below we have shown the cost functions for modified constant modulus algorithm and also the DDLMS cost functions. Now, essentially in the equalizer, we have to minimize the cost function using an iterative process. And in both the cases, we have to minimize the cost functions. Now, once we employ the output of the MCMA phase, each of the branches will go through the same iterative minimization process of the cost function, respective cost functions, and the output of every stage of the DDLMS stage will form the input to the, again, that corresponding branch of the QHLRT likelihood function determination. So once we determine the likelihood function value for all the candidate modulation schemes, we employ the modulation classification decision rule. Now we maximize the decision by the by examining the hypothesis for all the modulation schemes, and the maximum value will tell the corresponding modulation scheme. So this is about the complete scheme, and we will get into the further results and what is the specifics of implementation of this particular approach. So let us see the scheme results here. In the top two diagrams, we have the received signal and the output of the MCMA phase. So in the MCMA phase, we have already seen that there is a good amount of phase correction as well as amplitude normalization achieved. However, we have seen that the resultant constellation is still having a spread out due to the residual noise. Now, the result again for the DDLMS alone when applied to the DDLMS equalization phase, and the last figure, that is figure number 4, shows the output of the combined scheme. So, combined scheme is nothing but the cascading of the MCMA and the modulation specific DDLMS. So, as you have seen, MCMA stage is able to correct the phase as well as normalize the amplitude. And in DDLMS stage, because if it is not modulation specific DDLMS, so the decision boundaries will always not adequately fit into the decision boundaries. In that case, the output of the equalizer will not be able to normalize as well as resolve the phase uncertainties. Now, figure 4, of course, shows a much clearer output with phase correction as well as the amplitude normalization. We now examine the results of the blind equalization method that we have adopted by plotting the probability of correct classification against the signal to noise ratios. Now, we have plotted this against two different fading scenarios. Rather, we can say two different severity levels of channel fading, which we here we are representing as H1 and H2. And we have taken the cases of a QPSK as a candidate modulation and 16 QAM as the other candidate modulation scheme. Now, the leftmost part of the plot shows the bunch for the QPSK, and the rightmost side is for the 16 QAM signal. Now, 16 QAM is a multi-amplitude modulation, whereas QPSK is a single amplitude modulation. So there are differences of results. What is to emphasize here is that for a modulation classification using only modified CMA, we have a result which is much inferior for multi-amplitude modulation schemes, which is here is depicted with 16 QAM signal. So this is a big achievement, and because MCMA is traditional MCMA is not able to resolve multi-amplitude as well as single amplitude modulations with the same effect. So this proposed scheme is able to resolve this particular scenario. Well, we have now fairly resolved the three different scenarios and mitigated the channel impairments for the simple case of propagation loss and the second case of multipath propagation with a static channel, and the third general case of complex channel with variations of parameters, which happens in a moving target or an interception system mounted on a moving platform. So we are equipped with mitigation measures for all different scenarios, and which results a much versatile blind demodulation stage with mitigation of channel effects. So far we have done the theoretical research on improvement of modulation classification in considering the practical aspects. In that process, we have first done the symbol rate estimation, and we have implemented new methods which can mitigate the fading related impairments as well as it is able to perform in a very low SNR conditions. Then we have done under the same adverse impairments of low SNR and multipath fading, we have done estimation of parameters for modulation classification and also studied the theoretical results. Then we have, of course, done the mitigation of channel impairments for a case of varying channel within the observation interval. So with this theoretical results, now it's time to implement and deploy the system. Just to consider the requirements and the design consideration. So we are looking for targets like military radios, microwave terrestrial links, satellite communication signals. In that, the range of modulations varies from BPSK up to several orders of QM, and also some amplitude phase shift keying schemes, which is used for satellite communication. So these are the modulation schemes that is considered based on the practical use of the target signals. Then bandwidth are also based on the practical considerations of the targets. In this case, we have taken 20 kilohertz to 40 megahertz. So the front-end system should be able to tune those these various bandwidth signals using filters. And MC methods, modulation classification method, we have adapted as log likelihood-based QHLRT. Pre-processing includes symbol rate estimation, channel mitigation using parameter estimation, and minimum analysis sample duration being 1 millisecond. This consideration is because we have to also address frequency hopping signals, which are agile signals which hops between different frequencies within a particular allocated spectrum. So depending on the normal targets, military targets that we encounter, we have taken a maximum hop rate of 1000 hops per second, which gives us a signal observation interval of 1 millisecond. Now below is the platform, hardware platform. We have input signal for the front end starting from 40 kilohertz to 3.6 gigahertz with preamplification and AGC stages. We have the digitization stage. From the digitization, we have the FPGA implementation of demodulation done in the FPGA block. And from there, we derive the baseband IQ samples, and it is employed for modulation classification and other pre-processing estimates. So finally, the result is end goal of acquiring the bit streams for further processing of next layers of the communication intelligence block. So this is about the overall framework of practical implementation of the common system, considering all implementations that we have done based on the research results for different scenarios, as we have explained in the previous slides. In the first deployment scenario, these targets are mainly mobile military radios, and normally these are either man-pack radios carried by soldiers in the battlefield. Sometimes it could be radio relay communication links set up between forward areas. And in some other cases, it could be PSTN, fixed PSTN communication microwave towers. So with these different scenarios, we have multiple effects that we observe from buildings, and sometimes in the vegetations, sometimes from the mountains or hillocks. So if the target is not moving very fast, we have a fairly well static observation interval in which the main effects are uncertainty of the gain as well as the phase offset. So this scenario has been mitigated already, as we have explained from our theoretical results. And the picture that we have seen towards the right is the actual intercepted signal, which was deployed in a city condition. And the target was other side of the city, and the received signal was a result of many multipath reflections. And finally, it was resolved using parameter estimation. And finally, the modulation classification has been conducted using the likelihood-based method. This second deployment scenario is very interesting. We have deployed our communication intelligence system on a small transport aircraft. And this was the case of the moving platform, whereas the target is static. The idea was to penetrate deep inside the adversary's territories and to pick up the required communication target signals. So while we deploy, we have a mixed terrain involving some hillocks and some plain areas. Whenever we have the interception in the line of sight, we normally encounter Doppler shift and some propagation path loss. Whereas when this aircraft passes behind some hillocks or some vegetation, at that time, it is a completely mixed effect of channel variation and resulting signal. When we finally process that signal, will within the observation interval, there will be a variation of the parameters. So this required, again, the scheme that we have proposed in our previous slide. For mitigation, we have used that employed cascading scheme of MCMA and modulation specific DDLMS, followed by QHLRT modulation classification. So to see the results, it's very interesting. Although the theoretical results say something, we have something for you, which is slightly different than this theory. And this is because there are a lot of license parameters that come into picture when we deploy systems in these scenarios. And sometimes it is very difficult to predict why there is a deviation from the theoretical results and the practically what we see. So here is the table of probability of correct classification again. Now we have shown theoretical values against static channel and the varying channel, and the possible Nicen's factors which led to the deviation from the practical values from the theoretical values. So as we have seen for 9 dB of intercepted signal to noise ratio, theoretical values says it should be a probability of correct classification is should be ideally 1. However, in static channel, where we have seen mainly effects of gain uncertainty and phase offset, it is fairly matching with the theoretical value. And at that level of signal to noise ratio, we also seen that in the varying channel also, we are able to resolve the channel mitigation with a fair degree. And this is also tallying with the theoretical results. Even though there is a presence of Doppler shift due to the moving platform. Now, as we reduce the signal level, let's say at 4 dB SNR, the theoretical value is again 1, and static channel, there is a slight deterioration that could be because of the effect of Nicen's parameters like Doppler shift and the less SNR, of course. And again, for the varying channel also, we have a deterioration with compared to the theoretical value, attributed to again the Doppler shift. Now, bring down the signal to noise ratio to 0 dBm. Here we see that the theoretical values being 1 dB again, 1 again. Static channel still deteriorated to 0.75, and varying channel is not giving any result. It is, in fact, not able to determine the modulation. So here we have seen the attribution of Doppler shift, fast fading, timing offset, and various other unknown aspects, which has resulted in such a difference between theoretical values and the practically achieved values. So this shows that practical implementation and the theoretical values, there is a gap. So the scope of work still remains to shorten this gap and also to improve the system for this kind of varying channel scenarios in much more effective way. Well, now we have come to the conclusion. We started with the demand. The demand was for implementation of our own communication intelligence system within the country with the available technology base. And we have got mixed success. We are able to deploy systems which are operational in various fronts used by various agencies of the order of defense forces and law enforcement agencies. And the deployment results are also very encouraging because in various scenarios, intelligence gathering is going on, and exploitation of all this intelligence is also being done for strategic purposes of the country. So must do was the scenario where we have to deliver. So there was still scope for improvement, and there are still gaps. So it's a matter of continuous improvement, and this process is on. Need now was the requirement. That means we had a very short response time. Still, within the limitations, it was done, and the systems are in place. However, to deliver it further and to continuously improve the technology, the need of the hour is collaboration, and the collaboration should be within the R&D, academia, and industry. In this regard, we have experimented many ways. We have divided the problem statements into smaller problem statements, and because if we give it to academia, most practically it happens that the problem statements are given to the MTech students, or in some cases for the PhDs. Now, to get a very fast response, of course, PhD is being a very longer duration research period. So we normally prefer this is being taken up by MTech students, and because we look for a solution within a 6 months period. So MTech is an ideal time period. So within his research time, the one particular problem can be given, and the approach and the guidance, of course, it will be approach should be guided by the thesis supervisor, and also the R&D organization also will be backing up in every stage. So there will be some milestones, there will be some reviews, and finally, once the deliverables are completed, it serves two purposes. One is the thesis for the MTech student. At the same time, the R&D organization will be getting the deliverable output, which can be implemented in the respective comment solution block. So this way we can make a very complementary ecosystem, which will be a win-win situation for R&D, academia, as well as industry. Well, that's it. Thank you very much. And once again, I would like to thank IIT Goa for giving me the opportunity for this talk. You can reach me at this email ID anytime. I would like to respond to individual queries through the email. And you can suggest any research topic of your interest, which can be taken up within the topic that we have discussed. And we will be very much interested to take it up and implement that in the solutions that we intend to take up in the future. Thank you very much once again.